Hello everyone and welcome. Today, we're going to dive into something really cool about numbers. We're going to look at the secret connection between fractions and decimals. I know, sometimes it can seem a little tricky, but trust me, by the end of our time together, you'll see a hidden pattern that makes everything click. You ready to crack the code? Awesome, let's go.
So where do we start? Well, believe it or not, we're starting with the guitar. You know how you press down on a guitar string to make different notes? Those spots have names. They're called frets. And we can actually describe those spots using math, using fractions. So a certain note might be at 3/4 of the string's length. Another one could be at 2/3. But here's where it gets interesting. Watch what happens when we turn those fractions into decimals.
Okay, let's take a look. So, 3 divided by 4, that gives us 0.75. See that? It's a nice, clean number. It just stops. But now look at 2 divided by 3. Whoa. We get 0.6666666, and those sixes just go on and on and on forever. Isn't that a little weird? Why does one fraction stop and the other one just keeps repeating? That's the big mystery we're going to solve today.
First things first, let's get some words straight. For those decimals that do stop, we have a special name for them. We call them finite decimals. Finite is just a fancy word that means it has an end. It has a finish line. So numbers like 0.5 or our 0.75 or even 2.1, they're all finite decimals. They have a clear stopping point. Simple, right?
So what about the ones that go on forever? You probably guessed it. We call them infinite decimals. Infinite means no end. It just keeps going. And our guitar number, 0.666, is a perfect example of an infinite decimal. But you know what? There are actually different kinds of infinite decimals.
Yeah, let's look closer at these forever decimals. Some of them seem totally random, but others are super organized. They have a little pattern that just repeats over and over and over again. And for these guys, we have an even more special name, repeating decimals. And that little part that repeats, we call that the repeating part.
Now, can you imagine writing 0.6666 forever? Your hand would get so tired. So, mathematicians, being pretty smart, came up with a shortcut. To show that a number repeats, we just write the repeating part one time and put a little dot right above it. So, 0.6666 just becomes 0.6 with a dot on top. Or look at 0.121212. The repeating part is 12, so we put a dot over the 1 and a dot over the 2. It's a super cool and easy shortcut, right?
Okay, let's get back to our big mystery. Is there a way we can just look at a fraction and know, before we even do any division, if it's going to be a finite decimal that stops or a repeating one that goes on forever? Yep, there is. There's a secret rule, and I'm about to share it with you.
All right, here it is, the secret code. It's all about the bottom number of the fraction, the denominator. Okay, first step, make sure the fraction is as simple as it can be. Then we look at the denominator's prime factors. Now, what are prime factors? Don't worry, they're just the basic prime numbers, like 2, 3, 5, 7, that you multiply to get your number. And here's the secret. If the only prime factors you find in the denominator are 2s or 5s, it will be a finite decimal. If you find any other prime factor, like a 3 or a 7 or an 11, it's going to be a repeating decimal.
Let's try it out. Let's test this rule. Look at 3 over 10. The bottom number is 10. What prime numbers multiply to make 10? Yep, 2 times 5. Is there anything else besides 2s and 5s? Nope. So our rule says it has to be a finite decimal. And it is. It's 0.3. What about 1 over 8? The bottom number is 8. Let's break it down. 8 is 2 times 2 times 2. Look at that. Only 2s. So it has to be finite. And it is. 0.125. Okay, last one. Let's go back to our guitar fraction, 2 over 3. The bottom number is 3. Well, 3 is a prime factor, but it's not a 2 or a 5, so the rule says it must be a repeating decimal. And that's exactly what we found. 0.666. The rule works.
Okay, so we're getting pretty good at turning fractions into decimals. But what about going backwards? Can we take a repeating decimal like 0.777 and turn it back into a fraction? Yes, we can. It takes a few easy steps with a tiny bit of algebra. Don't worry, it's not scary at all. I'll show you exactly how it works. Okay, so watch me do one first. Let's use 0.777. Step 1, we give it a name. Let's just call it x. So we write down x equals 0.777. Easy. Step 2, we want to move that decimal point just one spot to the right. To do that, we multiply by 10. So 10 times x is 10x, and 10 times 0.777 is 7.777. So now we have a new equation. 10x equals 7.777. You with me so far? Good. Now for the magic trick.
This part is so clever. We're going to take our two equations and subtract the small one from the big one. On the left side, we have 10x minus x. What's that? It's 9x. Simple enough. Now look at the right side. We have 7.777 minus 0.777. And look, that whole forever part, the 0.777, it lines up perfectly and just disappears. It cancels out. It's gone. All that's left is 7. So our big, messy, infinite decimal problem just turned into a super simple little equation. 9x equals 7.
And now we just solve for x. If 9 times x equals 7, what do? We just divide by 9. So x equals 7 over 9. And just like that, we found it. 0.777 is just another way of writing the fraction 7/9. How cool is that?
That was awesome. Okay, let's try one together now. How about this one? 0.353535. This time, the repeating part has two numbers, the 3 and the 5. How do you think that changes things?
If you're thinking we need to move the decimal 2 places this time, you are absolutely right. Since there are 2 repeating digits, we need to multiply by 100, not 10. So if we say x equals 0.3535, then 100x equals 35.3535. Do you see how that repeating part, the 0.3535, still lines up perfectly? That's what we want.
And now we do our magic subtraction step. Let's do it together. 100x minus x gives us 99x. And on the other side, 35.3535 minus 0.3535 leaves us with the nice, clean number 35. So we get 99x equals 35. In our last step, we find x. So x must be 35 over 99. You see, the pattern is exactly the same. You are doing an awesome job with this. All right, it's your turn to be the math superstar. Let's try converting 0.555 back into a fraction. Remember the steps we learned. Go ahead and pause right here and give it a try. I'll wait. Okay, did you get it? The answer is 5/9. If you got that, give yourself a big pat on the back. That is fantastic. We did it. We totally cracked the code. We've gone from guitars to secret rules and even did a little bit of algebra. Let's just take a second to go over everything we learned today.
Wow, we learned so much. So first, we learned that decimals can either stop, which we call finite, or go on forever, which we call infinite. Then we found out that some of those forever decimals have a cool pattern, and we call them repeating decimals. We also uncovered that amazing secret rule. A fraction makes a finite decimal only if its bottom number is made of just 2s and 5s. And finally, we learned that cool algebra trick to turn any repeating decimal back into a fraction.
You know, all these numbers we've been working with today, the ones that stop and the ones that repeat, they're all part of one big, happy math family. And that family has a name, rational numbers. So what makes a number rational? It's super simple. If you can write it as a fraction, it's a rational number. That's it. But this leaves us with one final, very interesting question. We know repeating decimals are rational because we can turn them into fractions. But what about a decimal that goes on forever and never repeats, like the famous number pi? 3.14159. It just keeps going with no pattern. Can a number like that be written as a fraction? Is it rational? That is a fantastic question, but it's a story for another day. Thank you so much for learning with me. You did an amazing job.